Today we're going to start the two-dimensional part of Chapter 2 for real. So Chapter 2 is 2D kinematics. And our 2D kinematics is going to be a lot like our 1D kinematics, the difference being, in addition to our motion along the x direction, now we're also paying attention to motion along the y direction, and we're dealing with both of those at the same time, which means we have two sets of variables. You know, we have an x velocity and a y velocity, we have an x position and a y position, and we also have two sets of equations. We have our kinematic equations in the x direction, we have our kinematic equations in the y direction. To make a full inventory, I'll write all these down. So in the x direction, the horizontal direction, we have x initial, x final. We have v initial and v final, but these are the velocity in the x direction, so we put x subscripts on them to distinguish them from the other ones I'm about to write. We have our x acceleration, and we have time. In our y direction, we have y initial, y final, v initial in the y direction, v final in the y direction, our y acceleration, and also time, but really these two times are the same if we're following the motion of an object as it goes from here to here, and we're looking at motion in the x direction as it, in going in this direction, it's going to the right and it's going up. But the time it takes to go from here to here is the same no matter if we're following the direction or if we're following the motion like this horizontally or like this vertically. So those times are the same. A quick disclaimer about these subscripts. I'm not super careful about what order the I and the X are in. Sometimes I write VIX, sometimes I write VXI, VX initial. So it's either an I or an F, and it's either an X or a Y. So it should be easy to tell what I mean, even if I flip the order of the I and the X in the subscript. Okay, we also have a full set of equations in the y direction. I'm not going to write all of those down, but just as an example for a couple, we have equations like y final equals y initial plus v y initial t plus 1/2 ay t squared, or vy final squared minus vy initial squared is equal to 2a delta y. That should be 2ay delta y. There should be a y subscript on the a there. And our other equations we can adapt similarly. All right. So before we start using these equations, I want to talk about vectors. So vectors are mathematical quantities that have a magnitude just like numbers do, but they also have a direction. And so what this means is if we have a physical quantity that has a direction associated with it, we can treat this as a mathematical vector. So things like velocity, where we have an object, moving in some direction, maybe up and to the right, we can represent that velocity with a velocity vector v, and we put an arrow over the top to show that this is a vector. Okay, it turns out there are a few different physical quantities that are vectors that we're about to deal with, but let's just think of vectors mathematically for just a second. Things that are not vectors, like normal numbers that we add, those are called scalars. So here's an example of scalar math, right? I have we'll say 5 plus 3. 5 plus 3 is equal to 8, right? In math using vectors, we don't just have numbers here, we have numbers and directions. And we can add them together. In other classes, you may learn about how to multiply or divide them. We're not gonna worry about that. We're just gonna worry about adding and subtracting them. So maybe we have a vector that's like 5 in the up direction. This is not the notation we'll use. I'm just saying 5 in the up direction is a vector, right? A magnitude and a quantity, plus 3 to the right, or something like that. So our two vectors are in different directions. So when we add vectors, we take them and we can imagine that these vectors are arrows, right, of length, whatever the magnitude is. So like this is a vector that's up of length 5. This is a vector that's to the right of length 3. Adding those vectors together is like if we were, walking on the 2D plane, following one vector and then following the other vector. So adding those together would give us something that looks like this, and we go from here to here. So the effect of adding these two vectors together is the same as if there was a single vector that looked like this at some angle. Okay, so we can add these vectors together. It's going to give us some other vectors. So this, this vector is the sum of those two vectors. That's sometimes called the resultant. And it's the details about it, like what direction it's in and its magnitude, we can figure out with a little geometry, right? So, without worrying too much about this vector is at some angle theta that we could measure, and its magnitude we can figure out from the Pythagorean theorem, because in this case, these two vectors are at a right angle to each other. So the magnitude of this is like the square root of 5 squared plus 3 squared, which is, 5 point something, I think. If we wanted to figure out this theta, we need some trigonometry, and we'll get to that in a little bit. Okay, so the picture for scalars, is like we have 5 things and we add, 3 things to them, and we end up with 8 things. Direction not matter. Okay, so where does this matter in physics? We have a bunch of vectors. Velocity is one of them. Acceleration is the other. We will learn about other ones later. Position is also a vector, but really we almost always express position just in terms of x and y rather than as a vector magnitude and direction. So this turns out to not be as important as velocity and acceleration. Okay, so why is this important? Well, velocity, if we have a velocity vector that is up and to the right, we can look at how much of that velocity is to the right and how much of that velocity is up, right? So this is like, in this case, this is in the plus x direction, this is in the plus y direction, and we know that the x and the y are perpendicular, so they're at 90 degrees to each other. So what that gives us is we can separate this vector into 2 parts or components, a part that is only on the x direction and a part that is only in the y direction. And we call those components Vx and Vy. And these are exactly the Vx and Vy that we're using in our kinematics equations, right? So when we say, what was it? V final x squared minus V final y squared equals 2, V initial x squared equals 2a delta x. These are this is the final x component of the velocity. This is the initial x component of the velocity. So whenever we have the x and y parts in our x and y equations, those are vector components. So being able to get from a vector to the components, or vice versa, getting from the components to the vector, that is, those are important things to be able to do. So again, how we do that, how we go from the vector to the components is another important thing. So let's talk about trigonometry for just a second. This is just a quick little math review. This vector has some magnitude, some length, and we show that with our like absolute value signs. So the length of this vector is just like the absolute value or the magnitude of our velocity v. Okay, so Vx on this diagram is going to be equal to cosine of theta times the magnitude of v. You can show that this is true from our definition of cosine, I guess. So cosine of an angle is equal to adjacent over hypotenuse. Adjacent is Vx, hypotenuse is V, and if we solve for the adjacent side, we get cosine times hypotenuse, right? Cosine times hypotenuse. Vy is equal to sine theta times the magnitude of V. And I should say, these are not necessarily equations that you should blindly use. I'm going to put parentheses around them. These only apply for this diagram as I have drawn it. If this was in a word problem, you might just as easily have been given this angle instead of that angle, and then this is not cosine and this is not sine, and you should draw your own triangle to figure out what it should be. It turns out if it's the other angle, they flip. This one is sine and this one is cosine. So that's something to pay attention to. That's a really common mistake people make. You can always get the right answer by drawing a right triangle using the angle that you have. All right. Yeah, so that's how we get from the magnitude and angle to the components. We already said how we get from the components to the magnitude. That's just the Pythagorean theorem, right? The square root of Vx squared plus Vy squared. This is always true. And the magnitude of our velocity, this is called the speed. So we talked about that, when we were learning about velocity, we said speed was like the absolute value of the velocity. Well, that's true if the velocity is in the positive direction or the negative direction. This is just giving us the magnitude of that. But it's also saying a little more, right? Like if our velocity is at some angle, the speed is just, it doesn't care about the direction. It doesn't care about how much is in the x and how much is in the y. It just depends on the overall length of that vector. All right. So lastly, if we wanted to get the angle theta on this diagram, let's go back to how theta was before. This is another equation I'm about to write that is not necessarily true all the time. It depends on exactly what theta we're doing. But in this diagram, the tangent of theta is opposite over adjacent. The tangent of theta is Vy over Vx, which means theta is equal to the inverse tangent or the arctangent of Vy over Vx. And I'm going to put parentheses around this again because, again, this equation is not always true. It depends on how we are defining our theta. Whether it's relative to the horizontal or whether it's to the vertical or whether it's from something else. All right. I'll erase this. So I'm using velocity as this example, but all of this same math stuff applies to acceleration vectors as well, and later on to other vectors we're going to learn about in chapters 3 and beyond. But velocity is where it's going to be most important in chapter 2, so that's why it's the example that I'm using. Okay, so for combining vectors, we might have vectors that are at funny angles that we are trying to add. We might have a vector like this. We'll call this vector A, and maybe a vector like this that's vector B. So I'm adding vector B to vector A by putting them head to tail. So the sum of these vectors is a vector like this that is vector A plus B. But if we knew things about A and knew things about B, how could we find anything about A plus B? Well, you could kind of imagine this being a tough geometry problem where you figure out this angle between them and use law of sines or law of cosines, we don't have to use those in this class, so I don't remember what they are. But what we only need to be able to do the following things in addition to what we've already talked about. So being able to find components, being able to use components to find magnitude. We need to know how to add parallel vectors And this is really easy, right? If we have a vector that's to the right and we add another vector that's to the right, we end up with a big vector that's to the right with a magnitude that's just the sum of those two magnitudes. So if we have a vector of length 3 to the right and a vector of length 4 to the right, we end up with a vector of length 7 to the right. That's as easy as we could possibly imagine. If one of these were negative, pointing that way, then we would have to add a minus sign. So if this was pointing this way, we'll just do that like this. So if this was minus 3 and 4, then we do have to worry about that, and we end up with a vector that's just 1 to the right. And if you're interested, I can explain why this is, but we're not going to worry about that right now. The only other thing that we need to be able to do is to add perpendicular vectors, which we've actually already talked about just in the context of vector components. So in other words, if I have a vector that's like this, vector 3 and vector 4 like that, they're at a right angle, well, now they are basically the components of this vector, which is going to have magnitude root 3 squared plus 4 squared, which by coincidence actually equals 5. Yeah, so on a picture like this, when we're adding two arbitrary vectors together, what we do is we split each of them up into their x and y components. So here we have vector ax, or component ax, component ay. Vector b is here, so we have component bx and component by. And then for our big a plus v vector, the x component of this vector is just ax plus bx. The y component of that vector is just ay plus by. And we know how to do every step of this, so we know how to figure out exactly what a plus b is for a vector pointing in any direction. Okay, last warning about vectors. Sometimes we will have vectors that are not pointing up and to the right. I know, it's shocking. We may have a vector that is pointing, we'll say up and to the left, for example. And maybe, just to make this a good example, let's say it's at some angle theta being measured from the vertical direction. And it has magnitude, we'll say it has magnitude A or something like that. And we would like to know what its components are, right? We want to know what ax is, or sorry, that's ay, what ay is, and what ax is. Okay, so for ax and ay, those are, the opposite and adjacent sides relative to this theta, but note that the x component is not the cosine in this case. The x component is opposite the theta, which means ax is going to be the sine, so ax equals a sine theta, the way we have this. Ay equals a cosine theta, again, the way we have it. There's one important piece that I missed, or I skipped over intentionally, and that is ax here is in the negative direction. So this component needs a minus sign. When we calculate ay, we should be getting a negative number for that part of the vector that is in the x direction. And this minus sign does not come out of the math of this triangle. It does not come out of the trigonometry. We have to do this ourselves. And the way we do that is by drawing a picture and looking at the components and being like, okay, this one's up, that's positive. This one's to the left, that's negative. I need to put a minus sign in there. It's probably good practice to also put in plus signs when you know it's positive, and that's just, being in the habit of putting a plus or minus sign on your vector components just reminds you to think about whether it's positive or negative, and you're less likely to miss a minus sign there. Not strictly necessary, but probably a good habit to be in. Some of you might be confused because it's like, wait, I thought we could get negative numbers by trigonometry. Well, you can, but only for angles bigger than 90 degrees. So if we were expressing vector A in terms of its angle from the x-axis, we'll call that theta big, then the sine and cosine of this big angle, 120 degrees or whatever, would give us the right plus and minus signs on those components. But it is rare that we would be given an angle like that. I generally give angles in problems from the closest axis, or something like that. So so you should be able to look for those minus signs yourself and make sure you're doing those correctly. That will be very important.